Right, good evening, everybody. So on a vacation day, we just meet. So today we'll discuss quickly because I know some of you have term exams as well. So we'll discuss about prisms. Now, generally in a prism, we normally talk about equilateral prism. So the general idea is you have two refracting surfaces, and the bottom surface or the base is a non-refractive. Is it non-refractive? But sometimes they will ask you refraction from that surface as well. Okay. So if you look at this carefully, if you take a prism, A, B, and C. If you take these surfaces A, B, and C, these are your refracting surfaces, and this is the rough surface. These are your refracting surfaces, these are the rough surface. Now, if you consider light travel, light will travel. This is an incident ray. What do you call it? Incident ray. Normal drawn here. This is the angle of incidence, I1. I1, standard notation, angle of incidence. So rarer, denser, it will come towards the normal. This angle is R1. Normal here, let's say R2. Denser, rarer, it will refract away. And this angle will take as I2. These are standard notations. Normally we use those notations. You can use any notation you want, but general notations are these. So angle of incidence, angle of refraction from AB, angle of incidence to AC, angle of emergence. Angle of emergence. So this is your incident ray. This is your incident ray. This is your emergent ray. This is your emergent ray. So you have the incident ray, you have the emergent ray. Right. Now look at this carefully. You can see at this point, I'll mark it in black, at this point, X, a deviation is taking place. So light ray will travel, here deviation takes place. There's a bending or changing of the path. Light ray is traveling here, Y. You can see deviation has taken place. So what happens is when refraction occurs, deviation of light takes place. What happens? Deviation of light takes place. So you're focused on the deviation of light here when it comes to prisms. To look at this carefully, again look. To take a point X, normal notation for deviation is delta X. So deviation at X, look at this carefully. If you extend the ray, here you have deviation of X. Now vertically opposite, I1 here, I1 there, here deviation of X. So your deviation is going to be I1 minus R1 clockwise direction. So you can see there's a deviation clockwise direction. Here if you extend this, here there is a deviation Y. So vertically opposite here R2 means I2 minus R2, that's your deviation. So deviation at Y is equal to I2 minus R2. I2 minus R2, right? So there's a deviation at X and there's a deviation at Y. So deviation at X, deviation at Y. Now the total deviation is the sum of the deviations of X and Y. If there are three places, then X, Y, and Z. There are four places, X, Y, Z, whatever, P, Q, whatever. So here both are in the clockwise direction, so you can easily add it. I1 minus R1 plus I2 minus R2. By any chance, if one was anti-clockwise, so you have to bring everything in the same direction. So anti-clockwise becomes minus clockwise. So it becomes minus. Here both are clockwise, so you can directly add it. So your deviation is I1 plus I2 minus R1 plus R2. Normally, you can take this as a relationship as well. Normally, you can take this as a relationship as well. Okay, no? So what's your relationship? Delta or deviation. Deviation of light. Delta deviation of light. Deviation of light. Deviation of light is going to be I1 plus I2 minus R1 plus R2. Okay. So these are your first point that we will consider. Point number one that we consider, light deviates in a prism. When light deviates in a prism, you have deviation at x, you have deviation at y. So what you can do is you can add the deviations. If the deviations are in the same direction, add the deviations. If the deviations one clockwise, one anti-clockwise, you can subtract. Bigger one minus the smaller. Both are anti-clockwise, adding. Both are clockwise, adding. So here both are clockwise, so we add it. Delta x plus delta y, there you go. I1 plus I2 minus R1 plus R2. You can get this or you can take this relationship in your calculations directly. Okay. So let's write this up. Let's write in a prism, deviation of light occurs. In a prism, deviation of light occurs from the point of incidence, to the point of emergence. The path of the light ray has changed. The path of the light ray has changed. The path of the light ray has changed. We can represent this as indicated below. Right, quickly write down. This is deviation at x. This is deviation at y. This is total deviation of light. Right now. So section revision now we have finished. We have finished refraction from medium to medium. We have done optical fibers, total interreflection, critical angle, critical reflection, all of that. Now prisms. Yeah, moving into important sections. Right. Okay. Now the second point that we consider is these angles. If you look at this carefully, here you have normal, so angle 90. Here you have normal, angle 90. So angle 90 here, angle 90 there. This is called your prism angle. A is called your prism angle. So if you take this one, that one, that one, if you take this angle here, angles in a triangle 180. So this is 180 minus R1 plus R2. 180 minus R1 plus R2. If you look at this as a triangle, R1, R2, this is 180 minus R1 plus R2. Basic trigonometry. Look at the second point. Second point that you will consider. If you take these angles, if I take angle at A plus angle at X, I'll name this O, angle at O, angle at Y, that is equal to 360 degrees because we have four sides. Whatever geometry, 4 sides means 180 multiplied by n minus 2. N is number of sides, so 4 minus 2 is 2, 2 times 180, 360. Okay. A is going to be prism angle. So A, prism angle. Prism angle. X is going to be 90. O is going to be 180 minus R1 plus R2. Y is going to be 90, 360. A plus 180, 90, 90, 360. 90 plus 90, 180, 180 plus 180, 360. Minus R1 plus R2, that is equal to 360. 360, 360 cancel off. R1 plus R2 is equal to prism angle. R1 plus R2 is equal to prism angle. Now you can modify the relationship here. Therefore, deviation is I1 plus I2 minus R1 plus R2 means A. There you go. Another relationship. Another relationship. Okay. It's like we can find the relationship between R1, R2 and the prism angle. Between R1, R2 and the prism angle. And the angle of deviation as indicated below. And the angle of deviation as indicated below. There you go. You can mark this in the prism and then do the calculation. Okay. Quickly work. I'll give you about 2-3 minutes. Don't take long. 2-3 minutes. right? Okay. So once you get this, you will realize that a very important connection. When angle of incidence changes, angle of deviation will change. Angle of incidence changes, angle of deviation will change. Of course, this depends on the prism angle. So if you take angle of incidence to angle of deviation, you have variation like this for a particular prism angle. Now, when prism angle increases, the deviation will also move up. We'll talk about it in a while. But here there is a minimum deviation. Minimum deviation, here I1 equals I2 and R1 equals R. So whatever the prism angle, I1 is equal to I2, R1 is equal to R2 at minimum deviation. At minimum deviation. So delta is equal to I1 plus I2 minus A. And also R1 plus R2 is equal to A. So you can say at minimum deviation, at delta minimum, R1 equals R2. R1 equals R2 means 2R1 is equal to A. R1 is equal to A divided by 2. If R1 is equal to A divided by 2, substitute there very carefully. You can build a relationship. Therefore, delta minimum, don't forget, R1 equal R2, I1 equals I2. So here you have 2I1 minus A. Take it to the other side. Delta minimum plus A is equal to 2I1. I1 is equal to delta minimum plus A divided by 2. Divided by 2. Now from this, we can find a relationship for the refractive index. Now at minimum deviation, especially for an equilateral prism. So if I take this as an equilateral prism, look at this board. At minimum deviation, the refracted ray is parallel to the base. So here I1, here also I1, here R1, here also R1. And the best part is, remember this XY is parallel to BC. So if you take the prism here 60, 60, 60, guaranteed this will happen. If you write the relationship, I mean, if you just basically write the relationship, when it's equilateral. Also, you can say NA sine I1, NG sine R1. What is sine A1? Delta minimum plus A divided by 2. What is sine R1? Sine A divided by 2. NG is equal to sine delta minimum plus A divided by 2 over sine A divided by 2. There you go. That is another relationship for the refractive index of glass of a prism. Refractive index of glass of a prism at minimum deviation, you can write it down. So remember this, when angle of incidence changes, angle of deviation will also change. I1 equals I2, R1 equals R2, minimum deviation. From here we can build a relationship for minimum deviation. At minimum deviation, here you go, for I1 and R1. Remember this, for an equilateral prism, at minimum deviation, light ray is parallel to the base. When it's equilateral, condition is when it's equilateral. Not for all prisms. Not for all prisms. Don't forget that. Not for all prisms. Only for equilateral prisms, it's going to be parallel to the base. And if you write the general equation, refractive index of glass can be found. Okay, now let's say when angle of incidence I1 changes, when angle of incidence I1 changes, when angle of incidence I1 changes, angle of deviation will also change. Angle of deviation will also change, as shown in the figure below. As shown in the figure below. As shown in the figure below. At minimum deviation, at minimum deviation, like this, I1 equals I2 and R1 equals R2. I1 equals I2 and R1 equals R2 for any prism, whatever the prism. I1 equals I2, R1 equals R2 for any prism. For any prism. We can find the refractive index of glass. We can find the refractive index of glass using minimum deviation. Using minimum deviation as indicated below. Using minimum deviation as indicated below. Using minimum deviation indicated below. For an equilateral prism, the light ray through the prism will be parallel to the base. For an equilateral prism, the light ray through the prism will be parallel to the base at minimum deviation. At minimum deviation. But this is not a necessary condition for all prisms. But this is not a necessary condition for all prisms. So it doesn't need to be like this for all prisms. Equilateral prism, light ray refracted inside the prism is parallel to the base. Not for all prisms, huh? Not for all prisms. Okay. Right now, quickly. Okay. Right. Okay, no? So remember now, when the prism angle changes, the deviation also will change. It will slightly move towards the left and move upwards. So because prism angle increases, when prism angle increases, so different angles, deviation also will change. Okay, no? Right. Okay. Now look at this carefully. Now, if you take a prism, depending on the prism angle, whether light ray moves out or not can be decided. Look at this carefully. A, B, C. Let's say A is less than critical angle. C is for critical angle. Critical angle. Prism angle is here. Now, condition number 1. I1 is 0. What do you mean by I1 is 0? Light rays are coming perpendicularly here. Here A 90 minus A, this is A. A is less than critical angle, so refraction will take place. Light rays will refract from AC. Light rays will refract from AC. Now, if you take I1 equals 90, light rays coming along the boundary. If light rays come along the boundary, guaranteed reversibility of light. Reversibility of light. So 90 here means critical angle. Let's say R2. You know R1 plus R2 is equal to prism angle. R1 is C. R2 is equal to A minus C. Now you can clearly see A is smaller than C. A minus C will be a negative answer. Don't panic. There is a meaning for negative. Normally, when we took R2, it was above the normal. Above the normal. Can you see? R2 was above the normal. Above the normal. If R2 is negative, it means below the normal. If R2 is negative means it means below the normal. That means you must redraw this carefully a bit. This is how the light ray will behave. Now can you see? R2 is below the normal. R2 is below the normal. R2 is below the normal. So R2 is going to be A minus C. A minus C negative means smaller because A is smaller than C. So A minus C will be even smaller. So refraction will take place out. There you go. I. So from AC, light will refract out. Light will refract. What do you learn on this? When R2 is negative, it has a meaning. Normal notation above the normal. R2 negative means it should be below the normal. So below the normal means it goes somewhere here. Below that normal, it goes out. But does it go out? A is smaller than C, so this is going to be the magnitude there is going to be smaller than the critical angle. Okay. Let's say we can show that when the prism angle is less than the critical angle, when the prism angle is less than the critical angle, for any angle of incidence, light rays will refract from AC. Light rays will refract from AC. So how do you show for any angle? For I equals 0 also show refracting. I equal 90 also refracting. For minimum angle, maximum angle refracting, any angle refracting. Okay. Right now. I hope you understood the logic. Understood the logic? No? Is it clear? Okay, put in the chat. Huh? Is it clear? Understood the logic? So if A is less than C, when I equals 0 as a refraction, I equal 90 as a refraction. Any angle of refraction, for any angle between I equals 0 and 90, refraction takes place. Clear? Is it clear? Right. Right up. Okay. Okay, no? Right. So A is less than C. A is less than C. We can take the next condition. A is equal to C. Same way as earlier. I1 equals 0, I1 equals 90. Look at careful. I1 equals 0. Here, if you draw the normal, A here also A is equal to C. Light rays will travel on the boundary. Light ray just emerges into air. On the boundary means just emerges. I equals 90. I equals 90. I equals 90. Light rays will go along the boundary. Here, critical angle R1 plus R2 is equal to prism angle. R1 is C. A is also equal to C. R2 equals 0 means goes along the normal. What can you say? Light ray emerges. Light ray emerges into air. That's right. Second condition. If A is equal to C, we can show that. We can show that for any angle of incidence, light ray emerges into air. Light ray emerges into air. So, quickly write down. Okay. Right. What's the third point? If A is, now next option is greater than C. Now greater than C means how much greater? So you have two important points. So let's take A is greater than C. I1 equals 0. I1 equals 0. This is your prism angle. I1 equals 0. Light rays coming straight. here A, total internal reflection takes place. Total internal reflection takes place. Total internal reflection takes place. Because A is larger than C. A is larger than C. Now when I is equal to 90, now how much larger? That problem comes. When I is equal to 90, now this problem comes. So we take A is equal to 2C and A is greater than 2C. Just double. Okay. If you look at this, A equals 2C condition. Let's check again. I equals 90 and I equals 0. Okay. I equals 90 and I equals 0. I equal not total internal reflection. So now light ray. So when A is larger than C, total internal for sure. I equal not. So here also you want, you can check. I equal not A here. A is equal to 2C, so guaranteed total internal. So A is larger than C, guaranteed total internal. What about light rays coming along the boundary? Here also critical angle. So R1 plus R2 equals 2C. R1 is C. So R2 is also equal to C. R2 equals C means, if I draw this carefully or rationally like this, here also C, here also C. Light rays will go along the boundary. So what can you say? Light ray just emerges. Light ray just emerges. What about this condition? A is larger than 2C, because A larger than C means I equal not anyway will not emerge. When 2C light ray just goes along the boundary. So that means you can make a small conclusion. A equals 2C goes along the boundary. Next one, A greater than 2C, let's see. A greater than 2C also, quickly we'll draw these two. I1 equals 0, I1 equals 90. Have a look. Here if you take I1 equals 0, here prism angle greater than critical, total internal reflection light. Here light ray goes along the boundary. Here critical angle, here R2, what's happening? R2 plus C is equal to prism angle. R2 is equal to A minus C. A is larger than 2C. I take a very small increase, 2.1 C, let's say. 2.1 C minus C, 1 C. That means R2 is greater than C. Total internal reflection occurs. Therefore, total internal reflection occurs. So nice. You come to a nice point. A is larger than C. I equals 0. I equals 0. I equals 0. Guaranteed light rays won't emerge. A is larger than C. 2C along the boundary. Greater than 2C total internal reflection. So along the boundary, total internal reflection. Then what can you say? Here you can come to a conclusion. Therefore, A is greater than 2C. Light rays will not emerge. Will not emerge. A is equal to 2C. Just emerges. A is greater than C, less than 2C. What can you say? Light ray emerges. Light ray emerges. Okay, no? But guaranteed for I equal naught, light ray will not emerge. For the bigger angle, it will emerge. For I equal naught, light ray does not emerge. I1 equal naught, light ray does not emerge. I1 equal 90, light ray just emerges. Here I1 equal 90, light ray does not emerge. So A is larger than 2C, light ray never emerges. A is equal to C, it just emerges at 90. A is between A and 2C, it will emerge. This is just emerge means this does not emerge, just emerges, guaranteed emerges. Okay, no? Right. So that's how it takes place. Is it clear? Understood. So when A is larger than C, I equal naught, it won't emerge. But I equal 90, it can emerge. So between C and 2C, light will emerge. Equal to 2C just emerges. Greater than 2C can never emerge. Clear? Okay. Let's write. Let's write. I'm sure we wrote this next one. When the prism angle is greater than the critical angle, when the prism angle is greater than the critical angle, for I equal naught, light rays will not emerge. For I equal naught, light rays will not emerge. For I equal naught, light rays will not emerge. But when the prism angle is between C and 2C, when the prism angle is between C and 2C, light rays will emerge. Light rays will emerge. Light rays will emerge. Come on. When A is equal to 2C, A is equal to 2C, light ray just emerges. Light ray just emerges. Light ray just emerges. Light ray just emerges. And when A is greater than 2C, and when A is greater than 2C, light rays will not emerge. Light rays will not emerge. Okay, you can show it. Quickly write down. The note is here, actually, the summary is here, you can write it. So don't worry. Draw it. Finish? Anybody still writing this? Anybody still writing this? Okay. Okay. So this is the summary. This is the summary. Yeah? Have you finished? Anybody still writing? Anybody still writing this? No one. Okay, great. So I think now you have a better understanding. If the depending on the prism angle, you can decide whether light rays will emerge into A or not. Okay. But generally, if A is double critical angle, 2C, guaranteed no light rays will emerge. Between A and C and 2C, light rays can emerge. Equal to 2C, light rays just emerge. Greater than 2C will never emerge. Okay, no? Right. Finally, you can also use prisms as reflectors, especially the 45, 90, 45 prism. Because total internal reflection can take place. Normally, critical angle for glass will be about 41 degrees, 48 minutes. If you take a right angle isosceles prism, see light rays come here. This is 45. 45 is greater than the critical angle. Total internal reflection takes place. Total internal reflection, so like a reflector. It will act like a reflector. So here also, if you keep it like this, here 90, here 90, here 45, here also 45. Again, it will act like a reflector. Total internal reflection takes place. Then it will act like a reflector. Here you can show. Here you can show. Let's say light ray is coming. Total internal of this point only the issue comes. So here reflector. What I'll do is I'll erase this. I'll show it in a different way. Have a look. Make sure that the reflecting surface is here. And right. There you go. Now what? Light rays will come here, normal, here 45. Total internal reflection takes place. So you can clearly see here, light rays are acting like a, or the reflection or pure reflection is taking place. Here you go. Here you go. Reflection can take place. Okay, no? That's right. We can also use a prism as a reflector. We can also use a prism as a reflector. We can use a right angle isosceles prism for this. We can use a right angle isosceles prism for this. Right angle isosceles prism, as shown in the following figures. As shown in the following figures. Draw. Okay. Can I change it to the next page? Okay. Can I change it? Okay. Right. Okay. Right. So if you summarize whatever you did today, so we spoke about how prisms refract, causes deviation, found a relationship for deviation, and a relationship between the refracting angles and the prism angle, connecting that to deviation angle. Then we spoke about how deviation changes with the angle of incidence. A special case is minimum deviation. I1 equals I2, R1 equals R2. Whatever the prism, this can take place. But if it's equilateral, the light ray through the prism will become parallel to the base. From there, you can get a relationship using minimum deviation for the refractive index. Different conditions can take place. A is less than C, guaranteed light rays will move out of the prism. But when A is equal to C, light rays emerge, no issue. A is greater than C, I1 equals 0, guaranteed light rays will emerge, not emerge. Yeah, I equals 0. When A equal to C also, it won't emerge. When A is greater than 2C also, it won't emerge. But for I equal 90, A equal 2C just emerges. A greater than 2C does not emerge. That means when A is larger than C, I equal naught won't emerge. A equal 2C just emerges. I equal 90. A greater than 2C, I equal 90 won't emerge. That means when A is between, or prism angle is between C and 2C, guaranteed light rays will emerge. So equal to 2C just emerges. More than 2C will not emerge. So between less than 2C, between C and 2C, light rays will emerge. Okay, no? Y equal 90. Also, you can use a prism as a reflector. Light rays will reflect due to total internal reflection. Okay, no? So there you go. That's the complete summary, section revision for prisms. I hope this was useful for you all. And when we solve problems in the revision class, you can look at this theory and come, and we can quickly solve all the problems. Okay, then keep working.